Okay, in this second part of the lecture, we're going to turn to assumption violations related to Gauss-Markov. And in particular, we're going to look at the problem of non-spherical errors. So we're going to be talking about Gauss-Markov assumption 2. So far, we've assumed that the errors in our model have a simple IID structure. So they have mean zero expectation. They have a zero expectation. And the variance is given in this form here. The variance of epsilon is sigma squared times the identity matrix. Now the zero mean condition is essentially guaranteed with an intercept in the model, so we're not going to say much about that, but we do want to focus on this assumption here, which we've referred to as the second Gauss-Markov condition for the estimates of the linear model to be blue. Now, errors that satisfy this condition are known as spherical, and the slide shows the variance structure. So we have a single parameter, sigma squared, multiplied through by the identity matrix. And the ones on this diagonal of this identity matrix mean that the variance is constant across our observations. That's one implication of Gauss-Markov 2. And the second implication is that the zeros in the off-diagonal elements mean that there is no correlation between errors for different observations. Now, when errors fail to meet this form, we're going to refer to them as non-spherical, so they no longer have this nice structure. And there are two common ways in which errors violate the Gauss-Markov condition 2. That is what we call heteroscedasticity and autocorrelation. So let's turn first to heteroscedasticity, a very common problem, and it's present when the error term has non-constant variance. It's defined in the slide. So the variance of epsilon I given xi is equal to sigma squared I. In other words, each observation can have its own variance, and that is non-constant, so it's not constant across observations. In matrix form, the way we're going to write this is we're going to define big omega as a positive definite matrix, and we're going to write the, but it's a diagonal matrix, and we're going to write the variance as being equal to sigma squared times this positive definite matrix. So what you can see is that under heteroscedasticity, disturbances are still assumed to be uncorrelated across observations because the matrix is diagonal. Its off-diagonal elements are zero, but the diagonal elements are no longer all equal. So each of these smaller omegas can be thought of as a weight, and each observation then can have its own error variance, sigma squared I, but the off-diagonal elements, as I said, remain zero. Now, one thing that's important here is we looked at transformations earlier in this lecture, and we could apply some concave transformation to the response, so we could take the log or the square root, and this will induce shrinkage of large values, potentially reducing heteroscedasticity, but it doesn't provide a universal solution. We can look at that a little bit further in the tutorial. But the key point is heteroscedasticity, the variance of the error terms, is no longer constant. Now, why should that be the case? Where does heteroscedasticity come from? Well, it typically arises when the variances of the error depend on the value of the covariates. And because the variance of the errors given x equals the variance of the response given x, heteroscedasticity is present whenever the spread of y is a function of x. The common sources of heteroscedasticity are listed on the slide. First, the variability of the response may naturally increase with its mean. For example, the variability of traffic flow or speed increases as demand approaches road capacity. Second, omitted variables or an incorrect functional form can cause the residual variance to vary systematically across observations. Third, aggregation of heterogeneous populations or groups with different underlying variances. And fourth, influential observations or outliers that inflate residual variance in parts of the sample. These are all potential sources of heteroscedasticity. So what I want to do now is briefly review visual detection and formal detection of heteroscedasticity The detail of the formal tests is included in the review slides, but it's not essential, not particularly important, so I'm not going to go through it in any depth. I want you to understand the principle of non-spherical errors and what they mean, essentially. The actual tests themselves, the detail is not so important, though we may look at this in one of our labs. Okay, let's look first at visual detection of heteroscedasticity. The most common graphical diagnostic for heteroscedasticity is to plot the residuals against the fitted values. A plot of squared residuals against fitted values or against individual covariates can also reveal whether the variance changes with the level of the predictors. The three panels that I've included in this slide show you what to look for. On the left, we have a random scatter with approximately constant spread shown here. And this is suggestive of homoscedastic error. So here we're plotting the error against the predicted value. In the centre, the spread of the residuals is increasing systematically with the fitted values. This classic so-called cone or funnel shape indicates increasing variance. And on the right, we have the opposite effect. The funnel or the cone is in the other direction. That is to say, there's a systematic decrease in spread as the residuals grow in value. But any systematic change in the spread of the residuals is indicative of heteroscedasticity. Now, as I said, I'm not going to go through the detail of formal testing, but I do want to give you the principles of how it works. And this is as follows. Visual detection only gets you so far. You can look at it, but it's not really a definitive way of determining if heteroscedasticity is present. For a more formal diagnosis, we're going to use a hypothesis test. And essentially, we're going to set the hypothesis test up in this way. The null hypothesis we're going to use is that we have homoscedasticity, so spherical errors. The variance of epsilon I given x is constant, sigma squared. And the alternative is that this is not true, that we have heteroscedasticity. Each observation potentially has its own variance. Now, assuming that the errors have zero conditional mean, the null hypothesis is essentially equivalent to saying that the expected values of the squared error given x equal its unconditional expectation. That's essentially what this is saying. So the test for heteroscedasticity then, what we want to test is whether the expected square error is related to one or more of the explanatory variables. It's as simple as that. And to do this, we're going to specify a positive function h for the squared errors, epsilon I squared equals sigma squared times h of z transpose I delta, where zi is a vector of known variables constructed using our covariates x, and delta is a vector of unknown coefficients. And we're going to actually estimate that model, and the null hypothesis of homoscedasticity then becomes a joint test of multiple exclusion restrictions, that is, that all of those deltas should equal zero under homoscedasticity. If the deltas are jointly zero, the squared errors are unrelated to the covariates, and the data are homoscedastic. That's the null hypothesis. And two standard tests are built on this idea that I've included in the review slide. Please take a look through these so that you understand them, and we'll look at them in practice when we do one of our labs. The first is called the Brausch-Pagan test, and the second is called the White test. Brausch-Pagan test and the White test here. I've introduced a slide here on the Lagrange multiplier test because it's actually used within the White test. So look at these, please, in your own time. Okay, let's now turn to the second violation of non-spherical errors, which is autocorrelation. Now, again, I've defined it on this slide. Autocorrelation is present when the error terms exhibit non-zero covariance across observations. That is, when the covariance of epsilon I and epsilon j given x is equal to sigma ij, which is non-zero. So autocorrelated errors have a non-zero correlation structure. Assuming they're homoscedastic, then this time our big omega has this form here. The diagonal elements are all 1, which means that we have homoscedasticity, but the off-diagonal elements are non-zero, and that's what's inducing a correlation structure between observations. So in the presence of autocorrelation, the value that epsilon I takes for one observation may have relevance for the value that epsilon j takes for another observation. And that means that there's a dependency structure within the errors. Where does autocorrelation come from? Autocorrelation arises whenever observations that are close in time, space, or within the same group share common unobserved influences, including correlation in the error term. And common sources are listed on this slide. So in time series data, and this is a very, time series data typically exhibit autocorrelation. Observations recorded close together in time often exhibit serial dependence. So we can think about daily traffic flows or travel times, for example. If traffic's heavy today, it might tend to be heavy tomorrow. In spatial data, observations located near one another tend to be more similar than those further apart. So traffic speeds on neighbouring links, for instance, might be correlated. And in grouped or repeated measured data, repeated observations from the same individual, vehicle, station, road segment, whatever we're looking at, can be correlated because they share common characteristics. And we'll return to this structure in lecture 8 when we look at mixed models, this idea of grouped or repeated measure data. So in each case, omitted variables or unmodelled effects, temporal, spatial, or group-specific factors, are a common source of correlation in the error term. But in this lecture, let's just focus on serial correlation in time series data, illustrating how it can be detected using graphical diagnostics and formal statistical tests. And time series autocorrelation is really the classic setting for autocorrelation that you often read about, certainly in an introductory course such as this. Okay, so serial correlation. In a time series, the error term epsilon t at time t can be correlated with its past values. That is, with epsilon t minus 1, epsilon t minus 2, and so on. And with future values, actually. And the correlation between epsilon t and epsilon t minus q is known as autocorrelation of order q, where epsilon t minus q is the qth lag of ET. It's referred to as the qth lag of the error term. Now, a popular and simple model for autocorrelated errors assumes a first-order autoregressive process that we denote as AR1. And the model is as follows. Yt is equal to x transpose t beta. Notice that we're indexing by t to denote time, plus epsilon t. But epsilon t is equal to rho times epsilon t minus 1. So it's called first-order autoregressive because it's only the first lag of the error term that we're assuming is correlated. So the error at time t depends on its own immediately preceding value, plus a fresh disturbance Vt, which is an IID sequence with zero mean and constant variance. The coefficient rho is determining the strength of the correlation between the errors over time, and we require the absolute value of rho to be less than 1 for stationarity, a technical condition that we won't go into, ensuring that the correlation structure doesn't change over time. Now, as with heteroscedasticity, we can attempt to detect autocorrelation visually or via formal test statistics. We'll consider visual detection first, and then look at one formal test, the test for AR1 errors via the Durbin-Watson test. So, visual detection of serial correlation. Uncorrelated errors should show no discernible pattern in a plot against time. If the errors are positively correlated, we may see what's called tracking in the residual. That is to say, adjacent residuals take on similar values. Now, the figure in this table shows residuals from a simulated time series with differing degrees of correlation. In the top panel, rho is equal to 0, you can see here, and that indicates there's no serial correlation. And you can see that because there's no evidence of any time-related trends. The residuals are moving up and down in a fairly random fashion. Let's now turn to the bottom panel, in which rho is equal to 0.9. So this has got heavy autocorrelation. And what you can see here, there's a very clear pattern of tracking. Runs of adjacent residuals are moving up or moving down together, indicating that there's a correlation structure in the residuals. The central panel shows a situation in which rho is 0.05. Still substantial correlation, but you can see that visual detection here is more difficult. There's some evidence of tracking that we can see here and there in the plot, but the pattern is much less clear. It's hard to detect by just eyeballing the data, and that's why we need to have formal tests for autocorrelation. Now, as with heteroscedasticity, I want really just to give you a high-level understanding of what the formal tests require, what they're about really, what it is they're trying to do, rather than go through the detail of individual tests, because we don't have time to cover that, and it's non-essential anyway. So let's just think, what's the principle of formal testing? Well, in a regression model, and we'll focus on the case of AR1 errors, what we're going to do is we're going to test the null hypothesis that rho is equal to 0, which is where there would be no autocorrelation. And we're going to test that against the the alternative hypothesis that rho does not equal 0. And the simplest way that we could do that is given in definition 8. This is the t-test for AR1 errors. First, what we're going to do is run the least squares regression of y on x and obtain the residual vector. We're then going to run the second stage OLS regression of ET on ET minus 1, the residual on its own lag, and we're going to obtain rho hat from that regression and its t-statistic. And thirdly, we could simply use that t-statistic to test the null that rho is equal to 0. So it's actually just as simple as that. Note that we substitute the OLS residuals for the population errors, since the population errors are not directly observable. And in the review slides, we provide some additional detail on a test known as the Durbin-Watson statistic, roughly based on that principle. So the Durbin-Watson statistic is the classic test for AR1 errors in a strictly exogenous setting. The statistic here, Durbin-Watson statistic D, is the sum of the squared differences between successive residuals defined by the square of the residuals itself. In large samples, D is approximately 2 times 1 minus rho hat. So if rho hat is 0, D is 2. If D is close to 0, corresponding to rho hat near plus 1, or close to 4, corresponding to rho hat near minus 1, the residuals are said to be highly correlated. And the sampling distribution of this statistic depends on the specific regression matrix X. To make the test easy to perform, Durbin and Watson established upper and lower bounds for critical values of the statistic under the null, and these are tabulated for testing rho equals 0 against rho greater than 0. If D is greater than 2, that is, we're testing against negative autocorrelation, we use 4 minus D in place of D and compare against the same bounds. So again, we can look at this in one of our, we can look at the Durbin-Watson test in one of our labs, but for the moment, this is really the simple principle I want you to understand about how we could conduct a formal test for autocorrelation.